So in the last lecture, I discussed how to optimize variational parameters which are used to code some wave function. And that can be done conveniently when the transformation which produces the wave function is broken down into 1 qubit and 2 qubit gates. The Hamiltonian is a different story. You have to encode the Hamiltonian using some operators, and as I discussed earlier, the decomposition into Pauli basis is convenient, and then you can use, say, the Jordan-Wigner transformation for fermionic problems, etc., etc. The wave function is a different set of variables in this what a Hamiltonian is separate. So here the notation which I use is psi is some function of theta I, and for 1 qubit rotations, if I vary one of the parameters, then the expectation of the Hamiltonian can be written as some trigonometric function, and which is very easy to minimize. And the procedure which I described goes through all the theta j one by one, keeps on minimizing it, and it takes some iterations to converge, but it is much better than trying to evaluate the gradient of the Hamiltonian and then move in that particular direction. We can also write the same expression as some different version where this two terms can be combined. Constant remains the same. So if you expand it out, then d times e cos theta will become this, and d times e sin theta will become this, etc. The only point for writing this is in this form, the minimization is kind of trivial. If d is positive, then this quantity has to be equal to pi, because minimum value of cosine theta is -1. And if d is negative, then this is 0. Maximum value of cosine theta is +1. So the whole thing gets solved rather trivially. Only thing is you have to make three measurements of the Hamiltonian to find these three constants in whichever way you write it. So the minimization problem is now taken care of. One can ask whether it is possible to devise a strategy where all these variables are simultaneously minimized. Um, that is not really true because the gates will appear on initial state in some sequence, even in the logic circuits, and you can't interchange the order of gates in quantum scenario, but you can say that, yeah, I will not do it one by one, but I will try to combine effect of multiple gates. What happens can be worked out without too much trouble as well. So the circuit which produces this wave function will be given by, so this is equal to u of all the theta I acting on some size 0. So I can write that that is what will be executed by a circuit. Start with some state, apply one gate after another, which is mathematically described by a tensor product. Okay. So now let us see what happens when I consider multiple gates, and the easiest situation is to consider the gates in some sequence, which is, well, it's the same sequence as whatever goes into the tensor product. And I can ask, I have executed so many gates and so many are remaining, whatever it is. So this u theta I as a product of three factors. I'm going to apply a iterative procedure which is similar to mathematical induction. So it can be broken down into some notation. Okay, u0, there is a rotation gate with a single qubit, which is some step t plus 1, and then u of t, which contains all theta I from I equal to 1 to t. This has already been executed. This is the next in line, and then this is remaining. So that is way we apply a quantum circuit. So having done this, I can now repeat the strategy of calculation of H, and it's the same thing which I wrote down last time, except that this expression is now different. Like last time I had written V, then R, then W. So it's little different, but then what is the psi 0? The dagger of this, so U T dagger R T plus 1 of minus theta T plus 1 U 0 dagger HK U 0 R T plus 1 of plus theta plus 1, and then U T acting on psi 0. And then what I did was group the terms together last time. So this was defined as some new wave function. This was defined as some new Hamiltonian, and this is just a conjugate of that wave function. So it's something that can be explicitly evaluated. So this I'll just call psi prime, then RT plus 1. And now since this is still 1 qubit rotation, I just expand it out into cosine theta and sine theta kind of terms, and it gives the expression where the expectation value is taken on a state where all the previous gates are executed, and this is the next one in line. So it's essentially going to come out in the same three terms, but acting on a little bit different manner. So you can rewrite it, and the structure is going to come out as a tensor products. So whatever sequence you chose for executing these gates, and they will all appear one by one in some form, and you can write the final result in terms of all the parameters which are buried inside it. And this how many constants are there inside here. So this just means that I construct a tensor product of all cosine theta, sine theta, and 1 by the usual ordered factors, and this says that for every of these terms there is one constant in front, whatever it is. So there are 3 raised to t plus 1 constants. And yeah, so if there are m parameters, whatever various angles, then you will get a linear combination of 3 raised to m terms. This is nothing complicated, just writing this expression in a particular order. Now the job is a little bit different, that you want to now minimize all these parameters simultaneously. Okay. It's a much larger space. Here there were only 3 and minimization was kind of straightforward. Now it's a larger number of parameters, and you can't just do it analytically as trivially as in this particular case, but you can say that, okay, I will do it numerically. That is also okay, but luckily there is a shortcut available, and that comes from the fact that whatever these things are, they are still simple sinusoidal functions. So I can calculate these functions b by solving a set of linear equations, but what I have to do is to find b, I have to invert this operator, acting on whatever is there on the other side. But this operator is something which is very familiar. I can arrange this as a Fourier expansion. And so I can take this and apply on the other side as a Fourier transform, inverse Fourier transform. If I can do that, then I will find what is the value of b, and the minimization problem is easy. The only thing is this is now a discrete structure, so I have to use discrete Fourier transform. So b can be found by discrete but because it's a discrete transform, I have to be careful about the periodicity, and that is equivalent to dividing this interval of 2 pi into 3 steps. I need 3 steps because there are 3 constants, and which means that I can take some value theta 0 plus 2 pi by 3 and theta 0 minus 2 pi by 3. It have to be equally spaced because I am applying this discrete Fourier transform, and it will get the periodicity after 3 steps. And that solves the problem that I will run this circuit for 3 different values of the parameters, all separated by 2 pi by 3 for every variable. So totally there will be so many different terms, but this discrete Fourier transform is a ready-made library routine available. I can execute it either in the classical version when m is reasonably small, or you can even construct it in the quantum version, Fourier transform we have gone through before. And so that the yeah. Gives some solution of beta, the variable b, but it turns out that because you want through this all the gates in some sequence, it may not be the absolute minimum. You still have to iterate the algorithm. And then you will apply again all the theta varied in a sequence, simultaneously minimize the set of variables you have chosen, however many you want to handle together. You need to set up some convergence parameter to satisfy that you do it multiple times and you reach some minimum value. So this is a alternative procedure where you can try minimizing over multiple parameters simultaneously, but it turns out that again in simple tests, doing it just one at a time does actually a little better job. It's just a question of that's the way it goes. Numerical convergence is always something which you have to test out. It's not going to guarantee that it is always faster in this way or slower in that particular way. So this is one solution or one extension of this particular method. There is yet another version, and you can construct variations. They are all simple exercises. So there will be certain problems where the Hamiltonian has a translational symmetry. It's common in many physics situations. You are looking for a chain of atoms or even a crystal, whatever it is. The Hamiltonian has translational symmetry, and then you expect that whatever this wave function you obtain, that will also have the same symmetry. And it doesn't have to be translational symmetry, but it can be other symmetry also. I'm just writing translational just because easy to construct. And in this particular case, all these parameters will be same. The whole thing is going to repeat, and this whole structure the expectation value of h because all these parameters, there was I here, but now they're all going to be equal, so it will look like tensor product of cos theta sin theta 1 raised to some power. So this is and one can rewrite it. These are just trigonometric identities in a slightly different form, which is easier to manipulate or rather minimize. You don't need to do all the Fourier transform business, etc. It's a little bit simpler. And that is a finite Fourier series. I should use a different variable. J S is this power. Because you are looking for solution which has the same symmetry as that for the Hamiltonian. It can be that there can be other solutions which don't have the same symmetry as the Hamiltonian, then this is not appropriate. But if I want to look for the solution with the same symmetry of the Hamiltonian, the construction will simplify. Yeah. So this is like a ordinary Fourier series, little bit simpler to handle compared to this Fourier transform, etc. But still, you can get multiple measurements and find out what the coefficients are. So the thing which is not needed is this iterations over multiple theta. It kind of becomes unnecessary because all of them are equal and the order doesn't really make too much of a difference. So this is basically easier to minimize. So that is one variation. Yet another variation which I thought of, it's not in the paper. I will write down the reference for this. I wrote it last time also. This is on archive. The paper discuss what you can do when there is a variational of the 1 qubit gate. But you can ask the 2 qubit gate, can I put a variational parameter there also and try to find minimum with respect to that for the Hamiltonian? Yes, it can be worked out without too much trouble. The convenient choice is the logic gate, which is called control Z, which has structure 1, 1, 1 and -1. This is the control part and this is the sigma Z, which is appearing in the remaining twin location, and one can extend this to what is known as a RZZ gate, which can be written as 1, 1, 1 and e raised to I theta. This is a parameter you stick in some variation of this control gate, and you can ask, can I use this gate in the circuit and then optimize this particular theta? So something reasonable to try out. The advantage of using this Z is these expressions, they have two properties. the gate can be applied either way. It's a symmetric between the two qubits. That's because only the one element of this gate is different than identity. Everything else is equal to identity. And the other thing which is diagonal. And the advantage of diagonal structure is that if there are multiple gates of this type, they all commute with each other because diagonal matrices commute. So this is something which is simpler to try out and see what this kind of jugglery produces. So it will give some expression for h. I have not worked it out, but it's not too difficult to evaluate. It will be some function of theta, and then you can ask which theta will optimize it. And I will just leave that as an exercise for you. So you can optimize it. And the only thing which you need to keep in mind is that the expression will be a little more general because the psi prime, whichever is sitting over here, it gave expectation value for this 1 qubit rotation, which is just in the 2-dimensional Hilbert space. Here, when you apply that gate, the equivalent of psi prime will be a Hilbert space of dimension 4, because these operators are 2 qubit operators. And so you will have some expression in terms of expectation value in the 4-dimensional Hilbert space, but 4 is not that complicated and there is only one parameter, so you can again figure out what is the corresponding of this ABC. There will be some parameters of this 4-dimensional Hilbert space, and you minimize in that. So that is something one can understand, and maybe if you introduce more parameters, you can do the convergence to the final number in a less number of iteration steps, and that can help in evaluating the expectation value of this Hamiltonian. Okay. So this is as much as I want to say about all these various techniques and how do they help in evaluating the various expressions in presence of errors, but knowing that errors are of certain type and so keeping them under control.
When we separate that gate at t plus 1, so is there any iteration going on in t?
Here there is no iteration. When you write it over there, it's just a sequence of operations. The logic circuit itself is a sequence of operations. So you don't execute all the clock steps together. You can't do that. You have to apply the gates in the first clock step, then the gate in the second clock step, etc.
So we can select the value of t.
Yeah. So it just gives a what you call inductive procedure. You evaluated up to time t, then what will happen at time t plus 1?
So U0 is independent of t.
Hmm?
U0 is independent of t.
Yeah, so this is already something which you have executed. It's already a function of all the previous choices of the angles that you have made.
So number of angles with respect to which we are optimizing, that number is t.
Yeah, so that is what I wrote down, that how many of these angles or the clock steps you want. If there are m steps buried inside this, at the end of this exercise, you will get all the 3 raised to m terms.
I'm still not getting what is t. Then we can select t according to which, how to select t.
Your circuit will have certain number of logic gates, okay, which I am labeling here m. Now I am going to apply them in a time ordered fashion one by one. I can't apply them together, they don't commute. Okay, the circuit is executed in a clock step fashion. So I have to go all the way up to m, but I will go 1, 2, 3, 4 till I reach that particular point. And I want to evaluate now what happens when I execute from time t to time t plus 1, what is the change?
All these are unitary gates, gate R and gate U.
They are unitary gates because that is what you have designed in the circuit.
So how R is different from U?
This is a combination of t time steps. This is just a combination of a single step. In a single step, only R appears, nothing more than that. That is by assumption that I am wearing only 1 qubit gate.
And what is the meaning of time ordering?
Time ordering is part of the circuit. A quantum circuit always has a time ordering.
We can select any ordering, one specific ordering.
You can not specific ordering, the algorithm prescribed by the algorithm.
Why U0 is appearing before R of R?
Hmm?
Why U0 is appearing before R?
That is something which you have not executed at all. Whatever is remaining, I call it U0. Don't like 0, put some other symbol. That's okay. But this much has been executed. This is the current step, and this is what will come in future.
So the 0 is not.
0 doesn't have these parameters inside it. That's all. So now comes a question that I have to cover that whatever 3 raised to m terms for m logic gates, etc. And how do I find a good way to generate the logic circuit? Okay. I just wrote down that the logic circuit is equal to this by some assumption, and then you can say that, okay, I will have to look at the problem and figure out where are the parameters and design the logic circuit appropriately. The question comes that, is there any way to find a good logic circuits where just by varying these parameters, I will be able to cover the whole space? Okay, so the important point is that if I find a good circuit which will work for all problems, here problem means choice of Hamiltonian, then I don't have to keep on redesigning it over and over again. I take the fixed logic circuit, only thing I change are the parameters. And then, well, in some sense, it is Hamiltonian can have all kind of structures inside it, and the important feature is that sometimes the Hamiltonian will produce a regular pattern. Sometimes it will go zigzag all over the place. It can look like a completely irregular scheme. And then, well, whether my circuit will work for both these cases, that is essentially the question. And answer is not fully understood, but what people have kind of devised by playing around is certain types of circuits work well. And what I'm trying to do is give some justification for that particular choice, which has kind of become popular, because it's not explained in detail in any of the papers. They will just put one circuit and say, we'll use this. Why? We don't fully understand. So I have a argument for that, and that is related to a related subject, but something which is useful to know, and that is a subject of quantum chaos. So there are circuits which can produce both regular and chaotic behavior. The circuit is some implementation of the evolution structure. Function of the parameters, which are this theta I. So this can help, because sometimes the solution will be well behaved and smooth, etc. Sometimes it will be fluctuating, but whatever it is, by wearing this, you will cover both these regions and you will find some optimal solution. So this choice, how to construct dynamics, which is regular on one side and chaotic on another side by varying various parameters, and that takes me to the topic of understanding what is the meaning of chaos. Okay. that is a separate subject in itself. What is classical chaos and what is its quantum version? It's a subject which has been studied independently and also in very much detail with a long history. I'm going to give a kind of summary of what is it that we call chaos. So the colloquial understanding is chaos is a system where you can't predict the future. Okay, but there is a mathematical definition. So what it implies is that small fluctuations magnify under and the consequence is that predictability is lost. And one of the common examples quoted is just weather. Something which you are very familiar with, but you can't predict what is going to happen after 1 month. Okay. Maybe you can tell what is happening in 1 day. And that is because the fluctuations magnify at a certain rate, but the time evolution is small, the magnification is still within some bound, and you can tell what is going to happen. Longer term, well, the magnification becomes so different that I have no idea, or rather I can't tell. And why these fluctuations occur? Because every measurement, whatever system is there, classical and quantum, there is never a precise value. The value, whatever you measure with some error bars. So that means you don't know that value, you only know some interval, and the interval is size of the fluctuation. What is going to happen to it, you don't know. Okay. So the way this thing is characterized is in terms of what are called so if I take some variable, say x at t, and a neighbor in or I would start with 0. Some two initial value, they are someplace here, and then something happens. It's some 0 and time t. And the mathematical characterization of this thing is this xt minus the difference measures the separation, whatever is that, characterizing this magnification. So that will be bounded or normalized by whatever is the initial state, but then there is a exponential divergence. Okay. This exponential is specifically the result of a generic system, and the reason for that is that at least for small enough time, any complicated dynamics you can Taylor expand, and then the linear term is what you are looking at, and if you then calculate the time evolution, which is basically a linear difference, and if you have done the expansion in terms of a Taylor series, the leading term is the exponent. Because if I have some phi dot is equal to something times phi, I integrate it, that proportionality constant goes in the exponent, a leading order. And this lambda, so they are called Lyapunov exponents, and the signature of the chaos is some particular degree of freedom among whatever these labels are. If they diverge, you call it chaotic. It may happen that there will be some degree of freedom which will converge. Lambda will be negative. And then you don't have to worry about any instability occurring in that particular direction. So this is essentially a quick summary of what is constructed in classical chaos. Now one can ask, can you generalize this description to a quantum domain? And the answer is you have to be careful, not very quickly. Otherwise, it will lose the essence of what is meant by chaos. So, the first thing which you notice is, yes, I'm going to do this evolution. So if I have psi the analog of this thing evolving to this with some quantum operator. And if I take it for the neighboring point with the same dynamics, then it will have the corresponding state. And now what is the measure of the difference between two vectors? Well, the Hilbert space analog is overlap. The two variables are close by, the overlap will be 1. If it will be farther away, the overlap will be less than 1. But now if you take that overlap of this with this, the unitary operator cancels out. So a straightforward expectation of something like this doesn't exist. So now one has to ask a different question. what really happens to a quantum state even in presence of the evolution rules which are dictated by quantum mechanics. Can there be a similar situation as this? And for that, you need to find a more general description of chaos, and that is obtained in the language of the density matrix. Okay. That it's a distribution whose size is governed by the Planck's constant. Classically, it will be a point, but here the Planck's constant is non-zero. And what one needs to ask is not the evaluation of the point, but the evaluation of the distribution. And with this caveat, yes, something happens to the distribution, which you can identify as a chaotic evolution. Okay. Fine. So now I have to go back to describing various properties of the density matrix and the distribution, and then ask the same question: what is going to happen its time evolution? So as I have mentioned earlier, without proof, but it's very much necessary to encode the distribution that rho has inherent symplectic structure. This is same structure as in phase space, and with pairs of conjugate coordinates. Incidentally, I can write down the reference to my own article here where these things are explained. But it's enough to understand that the space of a density matrix can be broken into pairs of conjugate coordinates. And for a block sphere, I had mentioned last time that these coordinates are just cosine theta and phi. And there is a cross product between the two, which generates the area of the block sphere. And these pairs of conjugate coordinates in quantum theory, they get quantized in the units of Planck's constant. So these are unit, okay, so quantization of area is there's a minimum area, and the minimum area, whatever it is the value is a constant. What remains true is that the area so this is the answer to what happens, that under time evolution in this phase space, there is a very general theorem by Liouville which says that the area cannot change. It's equally true in classical theory and quantum theory. What changes is the shape. The volume or whatever area can get distorted. Okay. So the answer to that question is that yes, the total area is not going to change, but it can contract in one direction and expand in another direction. Both those features will come together, and so this kind of behavior will come in pairs. One direction contracts, the other direction expands. And the contracting direction, we have no problem, it is stable, it's well behaved, but if there is an expanding direction, we will identify it with chaos.
Sir, when we talk about mixed state, can
Yeah.
we say there are discrete areas, means not continuous?
Yeah, for the purpose of this understanding, there is always a lot of unknowns about the environment, and you can put them in a mixed state behavior. But if you want to understand the dynamics, is that whatever is the interaction with the environment, that is responsible for producing the chaos. With a completely closed system, then nothing will happen. So you have to first look at the whole system, which has some kind of conservation, and then look at part of it, and whether the part of that whole system, whether some part is expanding and some part is contracting or not. So that is what you actually have to look for. But yes, the description will involve labeling something in a mixed state language.
Here we also talk about pure state. Pure state also show quantum chaos.
In the sense that one direction is contracting and one direction is expanding. I will give you an example of that, which will kind of clarify the situation.
Directions are these like domains in the phase space where the area or the volume is contracting or
Yeah, so you have to identify the direction, which direction is contracting, which direction is expanding. That will depend on the dynamics. So now let me write down the same structure that I have two separate states, psi and psi prime. The relative transformation is what I call V of t, and I have to study what happens to this particular separation as a function of time. The fact is very easy to write down in using the unitary operators because it is the standard evaluation expression in presence of Hamiltonian, and the standard sign convention is which one is plus and which one is minus. This one is okay. That the relative operator transforms by exponential of the Hamiltonian. It's whatever I can call it, u times v times u dagger. It's a similarity transformation. And the magnitude of this, because this is unitary transformation, it doesn't change. But something happens to it. Okay? It changes in direction, though not in magnitude. And if I now rewrite this in terms of an exponential operator, which is also possible because this stuff is unitary. You get a evaluation equation, which is nothing but Schrodinger's equation. This is how evolution looks like. It generates a commutator with the Hamiltonian. These are all standard results in quantum theory definition. Okay. So now one can ask, what does it have to do with the density matrix? And the answer is that this is that you calculate this evaluation of the density matrix, you will get the same equation, commutator of density matrix with the Hamiltonian. And that is not an accident. Okay, this is built inside the theory in whichever way. So the density matrix evolves in some way. This distortion in the wave function also evolves in the same way, and the two things are actually the one and the same, just written in different language. So that is why I said that if you look at the distortion of the density matrix as a function of time, you will understand what is this separation also going to do as a function of time. They are equivalent. And what happens, okay, so I have two different objects. One is this density matrix, and another is the direction of this separation between different states. And I can choose to diagonalize either one of them. So both of them are Hermitian objects. So I choose a basis for convenience that the density matrix make diagonal, then there are all description, all kind of things. This is a mathematical label of how many components are there. It is given in terms of so-called Cartan generators, and they are all traceless. So for n-dimensional systems, there are n minus 1 Cartan generators, and the remaining one is the identity operator. N minus 1 are traceless, identity as a non-zero trace. And so non-trivial situation arises when the density matrix and this operator do not commute. Density matrix is the state of the system. The operator is the direction of perturbation. And then this can produce a situation that non-zero commutator is a signature of quantum mechanics. It can happen all the time, and then the perturbation can get distorted in shape during evolution. If they are going to commute, then it is invariant. Okay? There is nothing fancy, and just like that overlap is constant, the separation will also remain constant. So now let me give a very simple example, and then the more complicated version, which is used in this quantum logic circuit, I can explain the next time. Okay. So and this is not chaotic but unstable, and this is so-called inverted oscillator where the Hamiltonian has a potential which is negative of this quadratic function. Okay. And the way it is relevant is because it is unstable. If you start out somewhere here or anywhere else, doesn't matter because of the translation symmetry. On one side you will fall off in one direction, the other side you will fall off in the other direction, and small perturbation over here can get amplified. As I said, this is not chaos, but it is instability which exponentially magnifies. And it is very easy to see the classical structure and then the quantum structure as well. So this is Hamilton's equation just by taking derivatives. The flip over sign basically results in both these signs being negative. Okay. So this gives a complete classical evolution. If you want to write in a two-dimensional space, it's you can write it as a matrix. So if you had a regular oscillator which is nice and periodic, the sign of one of them will be flipped, this one, in the usual case, but here both of them are negative.
Hamilton equation are different for this case?
Hmm?
Hamilton's equation are different for this case because of
Hamilton's equations are not different. The expression for what the Hamilton equation describes, you can work out by taking the derivatives of h with either p or with x.
I am taking q dot equal to del h over del p, then I am getting x dot equal to plus p.
This sign is flipped, so the force is basically the gradient of this term, and you have to work out whatever it is. So let me see, did I write it correctly? What are the equations? dh by dp is equal to x dot, and dh by dx is equal to p dot, minus sign over here. So what will happen in this case? Derivative of this, okay, I probably wrote both signs, flip it, doesn't matter. The point is that corresponding to the situation where the regular harmonic oscillator, one of the sign has flipped. Okay. And now you can, this is the first order equation, you can ask the integral of it, which is an exact exponential. What are the eigenvalues or eigenvalues of this matrix? One of them is +1, the other one is -1. Okay. So if you have taken the regular harmonic oscillator, then the eigenvalue will be, well, essentially both of them will be, so this is 1 and minus 1, the determinant will be equal to plus 1, both eigenvalues will be plus 1. Or rather it will be it will be imaginary, but doesn't matter. So, the point is, this is a signal that in this space x and p, one direction is going to contract and another direction is going to expand. Okay. So that is this unstable nature, and this is what happens in the classical case. So now in the quantum case, okay, you can write down this p and x in many different forms, but the convenient version is in terms of creation and annihilation operators, which immediately tells you what is going to happen, and the subnormalization I won't bother to write down. Convert it, it turns out to be, it's Hermitian all right, but turns out to be a square plus a dagger square. As in contrast, so ordinary oscillator had H proportional to a dagger A. The sign flip is this because essentially x and p are a plus a dagger and a minus a dagger, and you square both of them and take a combination which is relevant. In one case, this a plus a dagger and a minus a dagger, you will get the difference which will produce this, another it produces a sum which will produce this. And now you can realize what this operator does. Okay, so e raised to I you have to remember stuff that you probably encountered in quantum optics. It's a squeezing operator. What has been routinely used to define squeeze states. Okay, and it demonstrates that the one direction contracts, the conjugate direction expands, total area does not change. And this is going to be the generic story. Which direction is going to expand and which one is contract? Well, you have to look at the Hamiltonian and the corresponding structure, but in a more general situation, the story is going to be the same. You will have a description of a quantum state. In one direction, you will have a positive eigenvalue, other direction have a negative eigenvalue, and then you will associate the positive eigenvalue direction with an unstable or in general chaotic evolution. The other one is a stable evolution. And in a more general situation, I will explain this next time.